Okay, the cellular technologies, as we mentioned last time, are standardized by ITU and IEEE. And among the different branches, currently 3GPP branch is clearly winning. And these are the technologies standardized by 3GPP. The 2G technologies are almost obsolete, and 3G is has the largest still has the largest deployment, but 4G is just replacing. And you must have noticed that the phone display has the generation number. Okay, and the generation number on the display, on the phone display, does not always exactly relate to what generation you have, like the LTE technologies. These days, some of the 4G technologies are available in our country, but until recently we had 3.9G, although it was called 4G, and that's not the case only in our country. Almost everywhere in the world, even in USA. For example, when people started you have, after this 3.5G, you have 3.75G. Well, maybe I just mentioned the names, or probably I did it last time, that you have HSDP and then HSP Evolution or HSP Plus, which was strictly 3.75G. Okay, and on the display, it appears as H plus. Now, when it was introduced, they started calling it 4G even in USA. Okay, and the operators, because and that's how they could have a better market in the. The operator which first introduced it started calling it 4G. So anyway, for it's all about money. So for better marketing, people call it. And I told you last time that the WiMAX we had was also called 4G. So the LTE we had was called 4G, but it wasn't, strictly speaking. So anyway, but these days a lot of LTE advanced features are implemented, and we can call it 4G. And 4G plus is a a a variant of 4G, when you can have one of the LTE advanced features, which is called carrier aggregation, in short CA. In this case, a lot of bandwidth first has to be available, and each of the maximum 4G chunks can be 20 megahertz. But with this carrier aggregation, multiple such chunks are 20 megahertz. Okay, or it can be each of the chunk doesn't have to be the maximum size for 20 megahertz, but when you can combine multiple chunks uh, to have a very large bandwidth, is called carrier aggregation, and that allows combining up to 5 chunks. And if you use the maximum size 20 megahertz for each of them, then it can be 100 megahertz at the maximum.
Sir, could
But
you
yeah,
repeat this part, sir, if you don't
yeah,
mind, sir? This
yeah,
carrier
yeah.
aggregation thing, sir.
I will. I will. Although I mean, uh, we it's not the uh, right moment, or it's not
Okay,
worthwhile
okay,
to discuss these things in detail, because mostly the details are covered in the cellular communication course. I'm just touching upon these things because there are a lot of things to discuss. Okay, I'm just touching on this thing because I have shown here 4G plus that appears on the display if the phone also permits. Okay, so just to explain the difference between 4G and 4G plus on the display. So the same phone will show 4G plus when you are using carrier aggregation. Okay, when you are using carrier aggregation, then it will show 4G plus on the display. But the good phones will do, not the ordinary phones. And that you get, I mean, this carrier aggregation means that, I mean, normally you have a particular carrier, right? You know that the operation uses a particular carrier, but multiple such carriers, or you can consider it as chunks of bandwidth. So multiple such frequency ranges or chunks of frequency ranges can be combined to have a very large bandwidth, of course, to support a very high data rate for a particular user. An individual, if requires very high data rate, he can be allocated a combination of multiple chunks. Okay, and then if it is done, he is actually using carrier aggregation, and then his phone will display 4G plus. Okay, once you uh, are again switch to original ordinary service like a single carrier, 4G plus will disappear and you will see 4G only. Similarly for 5G, and I said that I mean, the wireless side of 5G use is called new radio, or NR in short. Uh, Uses 5G on the display, but it has to a 5G for the first time allows the use of very high frequency. Okay, all the I mean, so far all the different generations, or until 4G, all the generations have used frequencies always below 6 gigahertz. Okay, usually it is even below 3 gigahertz. We'll shortly discuss uh, the challenges with high frequencies. So they're restricted to pretty low frequency ranges, uh, up to 3 gigahertz. And mostly it was around 2 gigahertz at the maximum. But there are some services at little higher ranges, but always the specifications don't allow you to operate above 6 gigahertz. Okay, but only in 5G it does. It allows uh, to use higher frequencies, and when you have high frequencies, it allows up to 100 gigahertz. Okay, but so far frequencies around the 28 gigahertz is the high frequency option. Okay, but there are a lot of activities going on or preparations going on at some other high frequency ranges. But anyway, when you restrict your 5G operation to the old low frequency ranges, like frequencies below 6 gigahertz or so, okay, then the phone will display 5G as usual. But if the same phone, okay, I mean, sometimes you may be switched to that high frequencies when you need a very high data rate. The same operator can have services at the legacy old frequency, legacy low frequency ranges, or the high frequency ranges. So it can switch to high frequency ranges optional to since the customers who require high data rate. And when a particular individual is using the high frequency ranges, maybe 28 gigahertz or higher, then this type of frequencies are called M wave. Will shortly, I mean, mention this name formally, and then you call it wave, and you uh, uh, I mean the phone will display 5G plus. Okay, so you don't expect it in our country anytime soon. Okay. One of the major reasons is that our policymakers are, miser the about letting people use the frequencies. Okay.
Sir, if
Yeah.
you don't mind, sir, me
Sure.
interrupting, sir. Sir,
I never mind for
sir,
if you
oh,
interrupt. So just feel free to do
sir,
that.
sir, when you were, sir, answering the career aggregation part, sir, I think my internet got disconnected a little bit, or yours. Like there was a
Oh, really?
yes, sir, like a gap there. So could you kindly repeat, sir, what is career aggregation, or why aren't we learning it up here?
I can, but uh, is it
Yes, sir.
uh, how about if I uh, continue with what
Yes, 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 sir. No problem, sir.
I mean, and later you
Okay, sir.
check
Yes, sir.
the uploaded file. Okay.
Okay, sir. Yeah.
So once I upload it tonight,
Okay.
uh, check it. If you still find that that part is not clear, then
Okay.
tomorrow I'll discuss that part again. Okay.
Okay.
Okay. So just shortly after the class today, I'll upload the file. Okay. Especially because that part is not very important for this course. Okay. Anyway, well, I think I also started discussing this one. Okay, I forgot. Uh, anyway, whoa, I think we came up to here last time. Man, I just forgot. Okay, so so you know that we have release 6. Okay, being released currently. Release 16. Sorry. Okay, so probably we finished all these things. Oh, we actually completed this whole presentation. Oh man, I forgot. Right?
Yes,
We,
sir. Probably, sir. Yes, sir.
yeah, we
Yes.
completed. Okay. So let me move to the next one. Okay, we'll have a quick discussion uh, on the comparison between the use of low frequencies and high frequencies for the wireless communication purpose. Okay, not for the use in circuits. Okay. Now we modulate the information signal and put it on a high frequency carrier. And we already discussed the purpose, and you guys answered it correctly. Okay, this is because you are at this university at IUT. Okay, in most other universities, people learn the wrong. I don't know why, but that has become prevalent in our country. So the purpose of modulating onto high frequency is twofold. You separate the transmissions uh, from different sources, okay, by modulating them onto different frequencies. And secondly, it allows you to use small. You can just calculate with say small frequency, like say if you calculate with the power frequency is 550 hertz. Okay, uh, c equals to f lambda. C means the velocity of the light. Okay, we'll also shortly actually officially show this formula, uh, c equals to f lambda, but probably most of you are aware of it. So with that, you can calculate lambda, the wavelength. Okay, that will be several thousand kilometers, because as you when your f lambda is a constant, as you have low frequencies, you have large lambda. Now the antenna is a we'll also have actually discussion on antenna tomorrow, inshallah. So the antenna is a has the dimension in the order of lambda. So when you have this kind of large lambda, your antenna has an impractical size. So you cannot use this kind of low frequency. I mean, as you say that your lambda is like several thousand kilometers. Okay. So uh, if you use high frequencies, then it is possible that you have a practical dimension for your antenna. Also, if you increase the frequencies, okay, if you make it even higher, then your antenna size further reduces, which is more convenient for you. The smaller or the antenna, the more compact it is, of course, it is more convenient. Okay.
Sir, can
Yeah,
you repeat
yeah.
again? Your voice got cut.
Oh, really?
Yes, sir.
Maybe my internet is not good today. Let me see if I I have two broadband connections. Let me check if the other is available. Guys, can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. I'm sorry. I mean, the other one is down now. Okay. I mean, that's why I have two. I, so even this one is not working well. Okay. So, I was just saying that the modulation, uh, you, I mean, transfers or translates the information, translates the frequency to a higher level. And as you have high frequencies, uh, S c equals to f lambda give you low dimension of low, I mean, smaller size for your lambda. And the antenna size is in the order of lambda or wavelength. So with high frequencies, you have a smaller dimension for your antenna. Could you hear me this time?
Yes, sir.
Okay. And we discussed it already, that it's a fallacy that raising the signal to high frequencies. Okay. I mean, most electrical engineers have this notion in our country. I don't know why. Okay. But the fact is that at higher frequencies, the signals die out at a shorter distance. Uh, so we'll discuss it today why. So
Sir,
yeah,
sir, is it the reason why the 5 gigahertz of 5 gigahertz band of the Wi-Fi router has lesser coverage than the 2.4
Yeah,
gigahertz?
right, right, right. You're right.
Okay, sir.
Thank you. So at low frequency, the signal can travel further. Now there are, so low frequencies are more attractive. When the government auctions the frequencies, people are more keen to lease the low frequencies. Lower frequencies are more attractive. I mean, if you have the same bandwidth, 5 megahertz, around 1 gigahertz will be much more convenient for you than 5 megahertz, around 2 gigahertz. If you compare with 5 megahertz, around 10 gigahertz, it will be far more. Uh, it will be far better for you. Okay, so let me show you why. So it is, first of all, it is low, it is more attractive. First of all, the free space path loss is smaller for lower frequencies. What that is? Well, see, the light from the sun gradually fades as you consider a planet at a further distance, right? I mean, of course, the light intensity is lower. But can you give me the reason? Is there any absorption or any loss of energy on the way as the wave propagates in the space? The sun emits light or energy. Okay, it's in the form of electromagnetic wave. So as the signal propagates in the space, which is like vacuum, there is nothing, there is no substance. So do you have any losses on the way?
Like, I'm not sure if there are, sir. We are not aware of it, I guess.
But sir, in the planets there is atmosphere, so
Yes,
there is a loss related.
in the
Uh,
planet, sir, yes, but sir, in space, sir, we don't know.
no, I mean, I'm talking about, say, if you are, well, if you consider a spacecraft, okay, you launch it from the, say, I launch it and it travels towards the sun. As it goes closer, the light or the heat, I mean, that will increase, right? The light intensity
Yes,
will increase, right?
yes,
Yes, sir.
As it goes further away, it will decrease. Or
yes, sir.
just consider any light source at your home. As you
Okay,
get
sir.
closer, definitely the intensity increases.
Yeah.
Right?
Yes,
So,
Yes.
okay, so in the space, that would also happen, I mean, consider any star. Okay, if the star is further away, its light intensity is also less. So, but there is nothing in the space to absorb the energy. So, how does the light lose energy? I mean, the space has no substance. So, does the wave lose any energy on its way?
like, sir, there must be some loss, sir, but I don't know what
Sir,
it's
the
called.
light is transmitted radially, right? So it will lose intensity over time.
Yes, sir. When we move further away, so and when we're closer together, there are like more beams of light hitting us. So that is why the intensity increases.
Yeah, exactly. Yes, I mean, it is emitting a certain amount of energy per second. Okay,
Yes, sir.
and when you just draw, I mean, visualize a sphere around itself, around the sun. Okay, at a short radius, then that power or energy per second will be distributed over this surface of the sphere,
Exactly, sir.
right?
Yes, sir. Yes.
And the same amount of power will be spread over a surface of a sphere with a larger distance, with a larger radius, right? So I mean the energy over per square per unit area will be less, right? I mean it will be 4 pi r square, which is sharing the same power, all the power from the or the energy per second from the sun. Okay, this power emission is not changing, but the surface area on which it is spread over will be different as you take different distances. So that is the reason.
But sir, is it a
And
reason for a loss, sir? Can
it
we
is
say it
not
is a
loss.
loss? It
It
is
is
not a
not.
loss.
It is not a loss in true sense.
Yes, sir.
It is not a loss in true sense,
Yeah.
but it reduces your energy reception,
Yes, sir.
right?
But it is
So
not a loss, sir.
it is not a loss,
not a
right?
loss.
Right. So, so it is. I mean, in literature, it is treated as loss. Okay,
Okay.
and it is called. See, the losses are also no losses are actually loss, right? All types of energy. Whenever you say energy loss, there is some energy conversion into another form. No losses are really, in truly speaking, no losses are loss,
Yes, sir.
right?
Yes.
So when you just, I mean, at your output end, you receive less, okay, whatever the reasons are,
Yes.
then you treat it as loss,
Okay.
okay. So you here this particular loss that we are discussing now, so just because of the distance, okay, is called free space path loss. Okay, I mean, as I said, that in the free space you have it. Uh, uh, of course, if it is not free space, if you have some substance filling in the space, then you could have other types of losses. That substance could absorb some energy. But the loss we are considering now is what you have even in free space. So this is called free space path loss. Please remember this name. And this loss, now we are saying that it depends on the distance. Okay. But we will shortly show. Okay, now I'm just stating, but we'll mathematically show you later that it also depends on the frequency. Okay. And actually, it depends the same way. You have, I mean, if you see the last line of, you can see the slide like free space propagation. Do you see the slide, free space propagation?
Yes, sir.
Okay. So the last line says that if you double your frequency, okay, then at half a distance, you receive the same power. Well, I mean, of course, I mean, if you consider two positions, okay, say 10 kilometer and 5 kilometer from some source, okay, from some radiating source, then the power will be higher at 5 kilometer. Now, if you double your frequency, okay, at this 5 kilometer distance, you you will get power that you were earlier getting at 10 kilometer distance. Got it? I mean, the frequency level and distance are affecting you similarly. Okay, as you, I mean, probably the explanation was not enough clear. Just if you have, I mean, it is like F into, say, frequency and distance. If you, I mean, the product of these two, okay, is
Sir.
takes,
Sir.
yeah,
Sir, is it like, let's say that I was giving 5 megahertz frequency and
Mm-hmm.
I was getting like 5 watt power
Mm-hmm.
at 10-kilometer distance.
Mm-hmm.
Now I have made the frequency to 10 megahertz. So
Mm-hmm.
I will get this 5 watt power at 5-kilometer distance, right?
Right, right. Yeah, yeah, exactly. With numbers, I mean, it's now probably uh, clearer, okay, for all the students. Okay. So that way it affects. So it's about free space path loss. The free space path loss affects this way. Okay. So we'll formulate and using, I mean, formula we will just demonstrate. So in other words, the path loss depends on the number of wavelengths. Okay, that the radio has traversed. I mean, how many? It's not like how many kilometers you traverse, like how many wavelengths you traverse. So that is always the same. With, I mean, 5 kilometer, 10 kilometer, or 20, 100 kilometer, your reception will change. But what happens? I mean, you always have the same amount of free space path loss with the same number of wavelengths. Okay, so as you change your frequency, the wavelength, say if you increase your frequency, your wavelength is shorter. So you'll have more wavelengths. So like say from 10 kilometer, when you uh between, I mean, in 5 kilometer distance, you have half number of wavelengths. Okay, with the example that you cited. But when you double your frequency, then within this 5 kilometer, you have actually you double your wavelengths also, because c equals to f lambda. Okay, you double your frequency means your you have half that size for your wavelengths. So now you have the same number of wavelengths within 5 kilometer that you earlier had for uh, lower frequencies within 10 kilometer. Okay, so you actually have, well, actually the formula will make it clearer. So let's wait until we show it. So it I mean, the free space path loss uh, can be calculated from how many wavelengths it covers. Okay, then there's the same. That doesn't change. Okay, so that is the most important reason why you have low frequencies better. Okay, I mean, better for reception. You lose a lot, I mean, more energy as you increase your frequency. Then penetration. We know that the energy we also receive in the buildings or around different obstacles, mostly because the energy can penetrate the walls or other objects. But of course, as you penetrate, you lose some energy, which you call penetration losses. These penetration losses will be less when your frequencies are lower. Are you getting me? The penetration losses you do have, but if you have low frequencies, okay, I mean, usually with most, actually it is not always the same. It doesn't treat the same way for all materials. For some materials, when you increase the frequency, I mean, it is erratic, I would say, but sometimes when you increase the frequencies, you can have smaller penetration losses. But mostly, for most materials, when you increase your frequency, you have more losses. So you have less energy at the other side of the object. Okay.
Sir,
So yeah,
gamma radiation has a very
yeah,
higher
yeah.
frequency.
We are talking about only radio waves, which has a frequency
Oh,
range
okay,
up
sir.
to 300 gigahertz. I know you are right. I mean, say X-ray or these things we do uh, because they have high penetration. Okay, they have high frequency, they have high penetration. but we're discussing the waves up to 300 gigahertz. Okay.
Okay, sir.
Even in, I mean, optical range, things will be a lot different. Okay. Attenuation by raindrops, especially when there is heavy rain, then the energy absorption by raindrops does matter. Okay, so there will be attenuation. The rain attenuates energy, or it absorbs energy from the wave. But again, for lower frequencies, this absorption will be much less. Okay, but when you use very high frequencies, and also you have heavy rain, then the rain works like a curtain. Okay, it takes a lot of energy. You may have to boost your transmit power. Okay. Diffraction, we know that allows you to have energy around some obstacles, because I mean the edges uh, sort of bend your signal. And if you have lower frequencies, then the angle at the other side can be higher, so it will bend more around obstacles. You have even I mean the new waves created on the, I mean from the edges, will have even higher angles. Okay, so you have better reception. Reflection usually also gives you better energy reflected, because the reflector will absorb less energy. The reflector reflects, but it also, I mean, some energy penetrates to the reflector. So it will, I mean, less energy will be absorbed or penetrated to the obstacle, and most of it will be reflected as you lower your frequencies. The Doppler shift changes your frequency, and that's the problem that can lead to some distortion. So if you have lower frequencies, then the Doppler shift is also less. Okay, we'll show it using formula later in this course. Okay, why you have I mean lower smaller Doppler shift at lower frequencies.
So when we are saying lower frequencies, or what is the range of a low frequency?
I don't mean any particular range. I mean, it's you compare all frequencies,
Yes, sir.
all radio frequencies. So frequencies from say just a few kilohertz all the way up to 300 gigahertz.
Okay, sir.
So you compare the whole range, and the lower frequencies are better for you from these respects. Okay.
Yes.
And last but not least, that your equipment will be actually a lot more expensive when you use high frequencies. Just the transmitting, both the transmitting and the receiving sides will be very expensive as you increase the frequencies. Okay. So you have challenge in signal propagation. You have challenge in how much power you can successfully receive at the receiving end, and also the equipment will be costlier. So so you always prefer lower frequencies. The lower it is, the better it is. That's it. Okay. So I mean, there's no particular low frequency ranges. The lower it is, the better it is. Well, now there'll be a question why you use high frequencies. Okay, you tell me first before I show you. Let me tell you,
It is because of the antenna.
because of the antenna. Yeah, you have just one advantage, only one advantage with the high frequencies, and that's like you have a smaller antenna. Yeah, okay, I agree with you. You have that, but you know what? When you already use several gigahertz, your antenna height is already enough small. Okay, you can, if you go for even higher frequencies, your antenna will be even smaller. That will be even more convenient, but that does not bring a lot of changes. Okay, it already fits in your device well, and that's not the main reason. You encounter a lot of challenges for high frequencies. Okay, so for this single advantage, probably you don't go for very high frequency. But let me tell you that the fact is, in the course of time, people are moving to the use of higher and higher frequencies. Like I said that for 5G, now people are using frequencies even around at 28 gigahertz, and there are a lot of activities for frequencies around 37 gigahertz, around 73 gigahertz for 5G operation. A lot of preparations are going on. So imagine 73 gigahertz. The specification, the original support in the specification is up to 100 gigahertz. Okay, but mostly, I mean, the frequencies which have been allocated so far are not that high. But in near future, people will be using frequencies around 73 gigahertz. I mean, very high frequencies. So why? So in the course of time, people are using higher and higher frequencies. So can you give me the reason?
Sir, data transfer rate is higher in if you use higher frequency.
Why is it higher?
Because sir,
Sir, higher frequency meaning, sir, greater bandwidth, right, sir? So more data can be
Right,
transferred in a
right.
smaller term
That's the
amount of time.
point.
Yes.
That's the point. We need, I mean, there is, of course, a rapid growth in the data rate requirement. All of you understand. The number of users is increasing, and every individual has a larger demand, okay, over time. So the overall demand is dramatically increasing. Now, this, to address the challenge of this increase, the technology itself is getting more advanced, is getting smarter, okay, to support higher data rate over a particular range of frequencies, over a particular bandwidth. The growth in the tech, like say 2G, 3G, 4G, 5G, okay, this evolution or advancement is allowing you to have is higher, I mean, which is called spectral efficiency. Spectral efficiency means how much data rate, how much bit rate you can support per hertz, okay, or over particular frequency range, say over 10 kilohertz, how much bit rate you can support. So this is indicated by spectral efficiency, and that's the key performance indicator. Okay, and there's the, I mean, key achievement in the evolution of these technologies, 2G, 3G, 4G. Okay, so BPS, the uh, unit for it is BPS per hertz, bit per second per hertz. So that's on one way that is affecting, but with a particular spectral efficiency, as you allow larger bandwidth, okay, so for example, if you have 3 bps per hertz, then with this strength, as you double your bandwidth, you will have double data rate support. If you can increase it 10 times, you will have 10 times increase in data rate. So linearly it will increase. We'll discuss Shannon's capacity later, which shows a linear relationship between bandwidth and the data rate capacity. Okay.
Sir, may
Yeah.
I interrupt you, sir?
Of
Sir,
course,
oh,
of
sir,
course.
we have been using the two words, sir, bandwidth and data rate, right, sir? So, sir,
Right.
more the ISP that so gives me the internet, sir, right, sir? So
Right.
I am taking a package, let's say 60 megabits per second, right, sir? So, like they usually give numbers like that, sir, right? So
Right.
if that is the number, sir, 60 megabits per second, okay. So, sir, they never give us the bandwidth, right, sir? So they're always giving us bit rate per second count. So
Yeah,
this is the bandwidth, right, sir, that they're providing us.
well, actually, I mean, we need to discuss the Shannon's capacity part to, I mean, to make it clear. But let me tell you now, I mean, uh, when I say data rate, okay, I actually
Yes.
mean the digital bits,
Okay.
zeros and ones. So it's bit per second, its unit is bit per second. In common speech, that is also called bandwidth. When they say they will give you 10 Mbps, so they will call it bandwidth. So but that is in the,
Yes.
they use, I mean, in common speech it is called bandwidth, but that is understood as the digital data rate. Okay.
Yes, sir. Okay, sir. Okay,
But
sir.
the I mean, strict bandwidth concept is, the frequency range. Say you allow the signal to use, say, I mean, around some carrier, say maybe 10 megahertz through 12 megahertz.
Yes, sir.
So this is the frequency range that you are using, meaning that your signal components, when you do a Fourier transform, you consider the Fourier components. So the signal,
Yes.
these Fourier components will lie within this range. There will be no components beyond that. They will lie within 10 to 12 megahertz range. That's what
Yes,
you are
sir.
occupying. Then your bandwidth is 2 megahertz. So for us, for electrical engineers,
Yes.
that's the actual bandwidth, the frequency
Exactly.
range. Okay.
Okay. So our
But
ISP, whatever they tell us, that is not the
that
actual.
is
That's the
actually, I
data.
mean, as I said that in common speech, that's also called bandwidth.
Okay.
I mean, it is not like you will be mistaken if you use
Okay.
that, if you call it bandwidth. Okay. But for technical people,
Yes, sir.
I mean, because they are not familiar with that frequency range,
Yes, sir.
they
Okay.
they experience the data rate. Okay.
So, sir,
So yeah,
my 60 Mbps that is being provided is within a bandwidth.
within a
Can I say it
bandwidth,
like this?
right?
Like
Of
it
course,
is within a bandwidth that they
of
have
course,
provided me with. When a
of course,
segment of their entire spectrum
of
is
course.
provided to me, which contains that data rate.
Yeah.
Okay, sir.
So that is definitely using a frequency range. That is a,
Yes.
I mean, it's lowest signal component. I mean, lowest frequency
Yes.
signal has a particular frequency, and its highest frequency component has a particular frequency. The range between them is your frequency range. Okay. And when it runs on, say, optical fiber, it's
Yes.
around some frequencies in the optical range, in terahertz.
Yes, sir.
And when it is converted, it is translated to Ethernet frequencies.
Yes.
Then it will be. Do you know that? Well, okay. I touch upon. I mean, shortly that would be my question. So, let me come on to that slide. Uh, so probably now it is now Shannon's capacity relates your digital data rate (BPS) and your hertz. I mean, frequency range. Frequency range has the unit hertz, right?
Yes, sir.
And for your digital data, the unit is BPS. So Shannon's capacity is equals to, I mean, in the next class, inshallah, I'll attach my writing pad.
Yes.
Uh, so uh, so you have I mean, I can tell you, if you can visualize, on one side is the digital data at maximum data at C. On the other side, it is B into 1 plus log 2 S by N. Okay. So here, I mean, on the right side, you have B, which is the bandwidth in hertz. Okay. So as you increase B, linearly, your data rate, BPS, increases. Okay. So anyway, so you have your I mean, spectral efficiency, your technological strength, and your signal to noise ratio. These three things affect. Okay, tomorrow I'll discuss that, inshallah, using Shannon's capacity. So these three things affect or they dictate how much data rate you will experience. in BPS. But that's your ultimate experience as a client.
Sir,
Okay, yeah, go ahead.
so you said that bandwidth depends on the frequency range, right?
Yeah.
So, sir, why you say like the higher frequencies, higher
No,
frequency signals
yeah,
have?
well, yeah, very good question. I mean, I'm saying, I mean, in the presentation today, I'm talking about the carrier frequencies,
Oh,
and around a particular carrier frequency, you use a frequency range for transmission, right? I mean, go back to your uh, telecommunication course last year. You modulated your information, and it took up a frequency range, right?
yes, sir.
So you'll have many, I mean, in the information consists of many frequency, like say if you use, say, uh, I mean, just think about double sideband modulation, okay? So you have lower sideband, you have higher sideband, and that gives a frequency range. You have to carry both lower and higher sidebands, okay? So it's a frequency range. Now, there'll be many components within your information, and they all will have to be modulated. So they will create all of their own sidebands. So you get a whole frequency range after modulation, and you have to carry the whole thing. Now, different people will be using different carriers. And that's how this whole range of frequencies that you use after modulation will be located at different positions of frequencies. The carrier could be only 10 kilohertz, it could be 1 megahertz, it could be 100 megahertz, it could be 100 gigahertz, right? The same bandwidth, maybe you are carrying 2 kilohertz bandwidth. Okay, your all the frequency components take up 2 kilohertz range. This 2 kilohertz range you can place anywhere around 10 kilohertz bandwidth or around 100 gigahertz bandwidth. Got the point?
Yes, sir. So, sir,
So
the carrier
where
frequency doesn't directly affect bandwidth. I mean,
it doesn't affect even indirectly.
oh, okay,
Never.
sir.
Okay, you have the same bandwidth. The bandwidth depends on how much information you have. Nothing else.
It's a difference of it's kind of difference of two frequencies, right? Bandwidth.
Mhm.
Is it a difference of two
Two
frequencies?
frequencies, definitely. Say,
The upper sideband and the lower sideband.
right. Say when you are after you modulate for every frequency component, multiple frequencies can be generated after modulation. Okay, and when you, I mean, your information is definitely, I mean, it's composed of many frequency components, numerous. So as you modulate all these frequencies, you generate, I mean, a whole range of frequencies, right? I mean, many frequency components are generated. The difference between the highest component and the lowest component is your total frequency range of operation. And that is fixed for a particular type of application. Usual, I mean, say, you know, that for radio broadcast, for TV broadcast, okay, for say cellular or for any particular type of application, the frequency range is fixed. The required frequency range is fixed, okay. But say, I mean, for radio broadcast, it is 9 kilohertz, and the different radio stations, or say your FM radio, it is 200 kilohertz. But the different FM radio broadcast stations use different carriers. They all use the same 200 kilohertz bandwidth, but that frequency range is located at around different carriers from different FM operators. Is it clear now?
Yes, sir. Yes.
Now, since, I mean, these operators will be using different carriers, some operators will have higher frequencies, some will be lower, like some will have around 90 megahertz. some will have around 100 megahertz, some will have around 105 megahertz. Okay, so they are using the 200 kilohertz bandwidth, but around different carriers, right?
Yes, sir.
So the frequencies they are using for transmission are not same.
No.
The people who are using lower frequencies are luckier. They will experience all these 7 advantages that we have finished explaining.
Yes.
Got it?
Okay, sir. One last
Yeah.
question.
Yeah.
Sir, so there's a lot of things happening in today's class. So initially, sir, we were talking about these 7 things are about the carrier frequency, right, sir? That we are getting,
Yeah.
right?
Yeah.
So
Yeah.
these
Yeah.
factors affect the carrier frequency. If it is lower, it is beneficial. So then
Right.
we moved on to the factor of the bit rate thing, right, sir? So
Right.
so this carrier frequency will be carrying some beats per second, and that is the bit rate. A bandwidth of bit rate will be carried, right, sir? Something like that.
Yeah.
Yeah. I
Yeah.
think
Right.
yes, sir. I got it. Okay, but sir, now, sir, if I move on to our let's say our Wi-Fi, right, sir? So
Mhm.
we receive that two dual band Wi-Fi's. What happens, sir? It has 2.4 gigahertz or 5 gigahertz. So is it like that's the bit rate that has arrived through a certain carrier frequency is now being distributed by other two new carrier frequencies? Is it kind of like that by our router?
Yeah. Yeah. Actually, the router transmits at around. I mean, there are different carriers in the around 2.4 gigahertz, and again different carriers around 5 gigahertz. Okay. So I mean, your device uses normally one of them, either a channel around two. Say,
Yes.
for example, if around 2.4 gigahertz, there are 11 carriers possible, but 3 of them you can have non-overlapping carrier, at most 3. Okay, so if you consider 3 carriers, okay, I mean, if I mean, there can be more carriers, but there'll be little bit overlapping. So anyway, so it checks which frequencies are available, which carriers are available. It uses one of them. Okay, and then 5 gigahertz will be another option. So you receive your data rate using one of the carriers. At a time, you receive the data rate using one of the carriers. So that carries the data rate. And the typical support that we have seen, okay, is much higher
Yes.
than our usual requirement.
Sir,
Sir, okay.
Mhm.
Ashraf, sir.
sir, is it something related to the channel of the Wi-Fi?
Yeah, yeah. So
Yes,
Wi-Fi has a say around 2.4 gigahertz. The total bandwidth available is like 79 megahertz. Okay, but you have there 11 carriers possible within this range.
sir, I have checked a few days ago.
I
My
mean,
Wi-Fi really has
I can be
40
little.
channels,
I mean,
and it is automatic
the numbers may not be
system
exactly
as well.
correct. The numbers may not be exactly correct. As far I remember, it's around 79 megahertz, and it is probably 11 giga channels. But if you consider non-overlapping, then at most there can be 3, around 2.4. Okay. Yeah. Yeah. What was your question?
Sir, my question is that like when we are saying that the Wi-Fi is transmitting its data at 2.4 gigahertz or 5 gigahertz, sir.
Mhm.
So uh, how is it different from all these things that we have discussed so far? It's like how is it different or similar? Like when we are saying that that data is being transmitted from the router at that gigahertz, so is it like what does that value signify? That 2.4 gigahertz or 5 gigahertz?
That is just the carrier.
Like another carrier has been
Yeah.
produced by the Wi-Fi itself in order
Yeah.
to
I
transmit the
mean,
data that has arrived there.
yeah. Yeah. I mean, the like you it supports, the router supports some carriers around. See, we have another presentation later that gives you that some frequency ranges are left by the authorities, okay, left for use with no license requirement. Okay,
Yes.
I mean, normally if you want to use some frequency, if you want to radiate, you need to I mean, you need to pay for it. You need
Yes.
to get a license for this operation, because somebody else also may need to transmit something, need to use some wireless communication. So if two people use the same frequencies, then nobody will be successful. There will be interference. They will interfere with each other, right? So the only way you can manage the use of frequencies in the air is to allow the use. I mean, is to introduce licensing, and that's the policy. Say all the FM radio stations, okay, have first got their licenses for operation in their channel, and they had to pay for it. The government leases the frequency chunks. So the cellular operators for all this kind of operation there. So these are this this is called licensed operation. Okay, but some small frequency ranges are deliberately left for use without any license requirement. Why is it so? For example, there can be many, say, devices. Say, yeah, you want to buy a remote controlled car for your boy. Okay, then is it possible for you to pay money to the government for this kind of operation? It is not, right? So there are many domestic use. Say your cordless phone, you can't pay for it. It's not possible. You have many medical equipment which uses which radiates energy. Okay,
Yes.
so it is called ISM, industrial, scientific, and medical. Okay, so these are the basic purposes, I mean, which is actually thought for this unlicensed band of operation. Now, these Wi-Fi guys are clever to actually take the advantage of this unlicensed band operation. So I'll show, I mean, one of our classes will give you the list of all these unlicensed bands. Okay, so there are unlicensed, these bands are not very wide. Okay, most of the frequencies are for licensed users, but some small range of frequencies are allocated around 900 megahertz, around 2.5 gigahertz, around 5 gigahertz, and quite a few other frequencies. There are like almost, in total, there are like 15 chunks of frequencies, okay, which are left for unlicensed use. Well, all the countries don't have, I mean, internationally they are unlicensed, but there are some difference in the uses of, in the policies of the governments among the countries. Some countries don't allow all these 15, okay? But anyway, this frequency around 900 megahertz or 2.4 gigahertz, 500 gigahertz, I mean, this kind of common, these are most common, and they are allowed in all the countries, okay? Now,
Sir,
this
Sir, I have a
sir,
these these Wi-Fi guys are using these unlicensed bands. That is why they have operation around 2.4 gigahertz and also around 5 gigahertz. Okay, so to take advantage of this unlicensed band, so you don't have to. There is no pin, but you know your cellular operation when you use mobile data, then it is on license band. There is, I mean, revenue for the government, but for Wi-Fi operation, there is no payment. Okay, yeah, go ahead, please. Walaikum
sir,
assalam.
sir, we actually forgot to tell you that we have a class from 10:15, sir.
sir,
Oh, really? Why is it
Yes, sir.
starting at
Sir,
10:15 today? Why is it starting from 10:15. I I'm supposed to get until 10:30, right? That's my right. I'm kidding, but anyway, is it
Yes, sir, but we actually forgot to tell you that.
okay? But why? I mean, is it off? Can it be officially scheduled at 10:15?
আর যে রমজানে 1 hour ক্লাস এর জন্য হয়তো 9:15 থেকে 10:15 ওই
Or is it 1 hour long?
Yes, sir. In Ramadan, sir. Yes, sir. That's what we know, sir.
Oh,
All
oh,
other
really?
Sir, I
classes.
need a help, sir.
Yes.
Okay.
Sir, can you please share the Google Classroom code? I've been asking for this code last week, actually. Google
really?
Classroom code. I didn't get the email that you sent.
Oh, okay. Please, do you have my phone number?
Yes, sir. I have your phone number. I called you.
Oh, really? I didn't pick it up. I'm sorry. Sometimes not sometimes, most of the time the phone is with my kids.
Can you please share
Yeah,
this in the chat
yeah.
box? The Google
Now
Classroom
in the
code?
chat box, I've shared my phone number. Please text me your email address. Okay. And let me stop now. So I'll see you tomorrow.
Yes.
Okay.
Inshallah, sir.
Inshallah. Thank you for your time.
Thank you, sir.
Assalamu
Assalamu
alaikum,
alaikum,
sir.
sir.
Wa alaikum assalam.